So thank you to the functional programming group for having me in this live coding session. I'm very excited to be here. And thank you, Ollie, in particular, for the invite. This is a wonderful opportunity for me to share some of the techniques that I've learned over the years on doing purely functional Scala development. And thank you to all the attendees who showed up, including the ones from the Scala Z mentorship program. I see a bunch of familiar faces, so thank you all for coming in and seeing what I'm up to. So today, I want to dive right into this live coding session that I've entitled FP to the Max. And the reason I came up with this coding session is because I feel like there's a lot of Scala developers out there who are very comfortable with FP in the small. So they know how to take a list and recurse on a list and do a bunch of things with a list or other similar data structures. But then when it comes time to taking these techniques of immutable data and pure functions and scaling them up throughout their entire applications, then they don't know where to begin. It's a huge gap between programming in the small and programming in the large. And it's really, really hard to solve that problem. One of the reasons is that you can't easily look at a 200,000 line of code application and get a sense for what that tells you about how to structure your own code. So even though there are purely functional applications out there, like some of the stuff I've done at my past two companies, they're open source, you can take a look at that. It's still not necessarily going to teach you how to do FP in the large. So I thought, well, why not do a big picture view, but on a very small toy example. And the goal would be to take a tiny little application that's written in a procedural style and then push it all the way. So push it all the way, use every single thing that as functional programmers in Scala, we end up relying on in order to build very, very large applications that we can understand, that we can test, that we can use equational reasoning and all these other good FP goodies on. And that's what this presentation is all about. It's about taking that tiny toy example and showing you FP techniques and principles that enable you to scale FP up to the largest possible application sizes you can imagine. Now, I have to preface this entire presentation with a disclaimer, which is that don't try this at home. I'm going to take a tiny little example, and I'm going to do stuff that, quite frankly, you don't need to do. If you're trying to obtain the actual benefits of functional programming, they're not necessarily going to apply to toy examples like this. And the reason is you can look at this code and you can figure out what's wrong with it and you can fix it, and you don't need to use FP at all. This is a small enough program we can fit it entirely in our minds, and we can simulate the entire state. And the lack of good types and the exceptions, all that stuff doesn't matter because it's just too small. And so we're able to deal with programs of this size quite simply without any of the techniques of FP. So even though there's never a reason why you would want to do this in the wild, it's my hope that you take a lot out of this presentation beyond the toy example that I'm going to show you, and that is techniques. So I want to show you that you can use FP to solve any type of problem, be it partial functions or side effects or looping or whatever it is you want to do. You can use FP to solve that problem that you have inside your business application. And also, I want to show you that FP provides very powerful solutions to problems of how we're going to model our business domain in a precise type-safe fashion. How are we going to minimize the cost of changes? In big applications, the cost of making changes is very, very high, and so we make very slow progress. Developers will write a couple lines of code a day and often still break things when that ships. And so one of the most powerful things that FP can do for us as we work in large-scale applications is minimize the cost of making those changes by empowering us to feel safe when we make changes to our software. and to use the compiler to help verify that the changes we made didn't break anything, and to use the types when we're working in a big code base to understand the functionality of our applications. And that's a very, very, very powerful benefit. And it's one of the reasons that people gravitate towards FP, because they love that feeling of being able to program fearlessly, just dive into a big code base, make changes, and know that it's going to work after the fact without having to run a bunch of tests and doing a bunch of debugging and all the stuff that you have to do typically when you're working on large scale, messy, imperative programs. I also hope that you get out of this that even though you run into lots of problems when you're doing software development, I would say that the answer to every problem ultimately is be more principled. It's actually don't cut corners. That's never the answer to any problem if you care about correctness and long-term maintainability of the software code base. The correct answer to all these problems is always going to be more principled in how you approach software development. And yeah, sometimes you write a little more code or add a few more type annotations or whatever it might be, but ultimately the code becomes much more reasonable and easier to understand, easier to change, and more comprehensible to a big team. So you don't have to rely as much on a domain investment, people becoming really good experts in parts of the code base, because the code itself will tell you so much about what it does just by looking at the types and reasoning about it using the tools that FP brings to the table. So with that said, we're going to go ahead and kick this off. If people have any questions, then please go ahead and use the Q&A tool inside BlueJeans, and I will try to pay attention to that as we go along. Note that the code has not yet been posted, so I will post the code for both of these, the before and after, as soon as we're done here. But if you're looking for it now, you're definitely not going to find it. So let's take a look here at this toy application. And if anyone can't see it, or if my screen's not showing for some reason, then please let me know here. This is the program, and it's written in a completely imperative procedural style. What the program does is it first prompts the user for the name, and the name is going to be used in various places in the program. First, it greets the user by name, and then it enters this imperative loop. It's going to execute continuously until certain termination conditions are satisfied. And what it does is, for every iteration in this loop, it's going to pick a random number between 1 and 5, and it's going to ask the user to guess what that number is. Then it's going to read a line of input and as a integer, and then if it's correct, if the user guessed correct, it'll print out one message. If the user did not guess correctly, it'll print out a different message. And then it's finally, just so this doesn't repeat forever, it finally asks the user, do you want to continue? And if they say yes, then it continues the loop. If they say no, then it exits. So very, very simple program, does exactly what you think. It's a number guessing game between 1 and 5. And it's just decorated a bit with the presence of this name here. But other than that, it's very, very straightforward. Now let's take a look at this and look at all the things that we can recognize here, which are problems. So one of them is this read line here. I actually played around with this program for a bit, and even though I wrote it, I succeeded in crashing it in like 2 or 3 different ways without even trying to. And the reason for that is there's a bunch of partial functions inside this program. And this happens all the time. If you're programming in the full Scala language, you'll accidentally create a partial exception, and then you'll end up blowing stuff up. And hopefully that gets logged and your customer complains about it and you're able to diagnose and fix that problem. But it's a very, very unfortunate state of affairs. And we're going to see that we actually have tools in FP to clean this up. And then, of course, there's another way in which things can go wrong, at least one other way. And then this read line here, this innocuous read line, it looks for a yes or no, but if the user doesn't enter in a correct input, then it's just going to crash here. So there's 2 ways this thing can crash, and I found both of them accidentally. I knew about them, I put them in here, but I encountered them accidentally as I played around with this program because it's so easy to get them wrong. So we're going to take and and eliminate these partial functions as our first step. And the reason why we're doing that is because in this presentation, I'm going to systematically show you how you can take an imperative program like this that does input and output, and that has various ways in which things can fail for very legitimate reasons. The user enters an invalid input, and also it carries around some amount of state with it. I'm going to show you how we can use pure functional programming in order to represent this application in a way that gives us a lot of benefits. How do we do that? Well, first I have to spend 5 minutes talking about what functional programming is. And what functional programming is quite simple. It's just programming with functions. So you build your program from functions and immutable data structures and so forth. And what functions are mathematical functions, so not procedural functions. A procedural function is a list of instructions that you send to your CPU, telling it to update this memory location and send something over the wire and so on and so forth. And mathematical functions are not like that. Mathematical functions have three very important properties that allow us, that give us a number of benefits when we're doing pure functional programming. And those three properties are totality. So every function is total. That means for every input, a function will return an output. If we send it an A, it's going to give us a B, always, no exceptions. And that's not true, obviously, for some of these functions here. This toInt function takes a string and returns an int. At least that's what the type signature says, but it's in fact line, because there are some strings we can send it for which it's not going to return an int. And that lie leads to runtime errors in our application, so it's quite serious. And then this other one is a partial function here. We're taking this read line, the string, and we're turning it into true or false. And we're kind of claiming here that we can handle all strings, but in fact we can only handle two strings, and it's going to crash on all the other strings. So this is an example of another partial function, a little bit hidden because it's in this match clause, but it's still a partial function. Math functions are also deterministic, which means for the same input, they return the same output. And that has lots of nice properties that enables you to reason sensibly about your program without having to keep in mind a bunch of state. And then finally, math functions are pure, which means they don't have any side effects. They can have effects, but their effects are limited to computing the return values. And there's a bunch of stuff going on in here that's not pure. We'll see that in a second. So these three properties, totality, determinism, and purity, they give us a number of benefits. For one, they help us reason about our programs using equational reasoning. And I encourage you to look that up if that's something you've not seen before. But equational reasoning just allows us to treat our programs as collections of equations. And so we can understand the meaning of any fragment through simple substitution. If x equals y plus y, then to understand what that means, we just substitute y into that expression. We inline it and we simplify it, and we can understand what that x program means. That property only holds for purely functional programs. It doesn't hold for imperative programs. In order to understand the meaning of a fragment of imperative software, you have to simulate the state of the machine inside your head, which is something machines are very, very good at, and humans are terrible at, which is why a lot of people say FP is good for understanding your software. It's because equational reasoning. They also, because of this property of being able to reason about our programs using equational reasoning, we can treat them as sets of equations. We're also able to refactor our programs safely. We can do inlines, and we can move stuff around, and we can just do all this different stuff, and it doesn't change the meaning of our programs because it's just a bunch of equations. And that's very, very powerful. You can do large-scale refactorings without having to think about it, and you'll come out the other side. And if it compiles, it'll probably just work. That's been my experience from 10 years of pure functional programming. Determinism and some of these other properties like purity, they also help us test our programs more easily. When functions always return an output, and it's always the same one, it enables us to test them in a much more rigorous fashion. And the inversion of control that you often see in functional programs ensures that the caller always has control over what the callee does, because the callee can only return a value, and the caller can choose what to do with that value, if anything. So the caller of everything has ultimate control in a functional program. And that inversion, that pushing power up and also deferring things higher and higher in the call stack, leads to programs that are much, much easier to understand because you don't need to drill down into the leaves of your program in order to understand the behavior. You can understand it high up because you have control and decisions are deferred to the maximum extent possible. That inversion of control is one of the most powerful reasoning properties that pure FP gives you. And then finally, I mean, this is not finally, actually, there's a bunch of other benefits I'm not going to talk about. But finally, for our purposes today, programming with these functions helps us reason about our program using type-based reasoning. So we can look at a type and we can say something about what that program does. That's not possible when you're programming outside the pure FP subset of Scala. If you program using just sort of vanilla Scala, and you use reflection, dynamic reflection, and all the other stuff that you can do, methods on object and so forth, you can actually break type-based reasoning. You can't look at something and know very much about it. And that's not great because type-based reasoning lets us look at a type and know what a function does. And if we don't have that property, then in order to know what the function does, we have to drill into its definition. And then it's going to call other functions. And so we're going to have to drill into their definitions and so forth. And that's why we spend so much time trying to understand code, especially code we didn't write, but even code we did write, but we just wrote however many months or years ago. It's a lot of work because of all this drilling down and trying to understand stuff and simulate stuff in our head. And in a functional program, we don't need to do that because the type tells us what it does. The type becomes a compression on the implementation, a lossy compression on the implementation of the function. And so we look at the type and it gives us boundaries for what that function can and cannot do. And oftentimes these boundaries, in a properly factored functional application, these boundaries are sufficient to allow us to understand what the function does without having to dive into its implementation. And that's very, very powerful. So here's some examples of functions that are not, they're functions in the programming sense, but not functions in the math sense. Printline, for example, it takes a string and returns unit. And this function is probably total. I don't know if this can blow up in Scala. Probably not. Something really strange would have to happen, like standard input would have to be disconnected or something for it to throw an exception. It is deterministic in the sense that you give it the same string, it's always going to return unit, but it is definitely not pure because it's interacting with the external world. It does more than just returning unit. It actually prints something to the console. And same for readline. Readline is, again, close to total, not quite, but almost for all intent and purposes. And it's definitely not deterministic because every time you call it, you could get back a different string. And then this one here, parseInt, is deterministic, but it is definitely not total. And it could be pure, actually, it is pure. So these two methods here, printline and readline, if we're to shift our minds over to the FP subset of Scala, then we can actually say a lot about these functions. And in this one, we can say the implementation must be unit. And in this one, we can say it's some string. We don't know what that string is, but we know it's going to be some string. And just being able to look at a type like this anywhere in your program and know its implementation, which, by the way, only holds if you're doing pure FP, like I said before, is extraordinarily powerful. So right now, if I saw this in an FP Scala program, I would know that its implementation is unit. And if I saw something like this in an FP program, I would know its implementation is something like this. I wouldn't be able to tell you what string it returns, but I would be able to tell you it's a constant string. And then I would be able to look at something like this and tell you that if you feed it any type of string, you're going to get back an int. So I don't know what that means for strings which are not numbers. Maybe it returns -1 or some other magical number. I can't tell you that, but I can tell you it's safe in an FP program with any possible input, and you're always going to get back an int. And these are very powerful guarantees that change the way you interact with your code because you're no longer afraid and you no longer have to drill down into things in order to understand it. All right, so let's take this knowledge of pure functions as total, deterministic, and pure and see if we can bite off some of the low-hanging fruit. in this application. So I've created a copy of the application here. And what we're going to do is we're going to eliminate the sources of partiality. I'm going to start here with this one here. So this is not going to be too difficult. This read line here calls toInt, and toInt can fail. So what we want to do is take this partial function and we want to lift it up into a total function. And there's a very simple technique we can use to do that. And it just involves using data structures like option or either to represent partiality and errors. So in this case, I'm going to define a function called parseInt, which is going to take a string, and it's going to return an option of an int. And it's just going to call try of s to int, and then to option that. And then down here, we'll call parseInt here. And then that changes this guess into an option of an int. So we have to do some other stuff here. Namely, we've got to do something like this. If it's none, we'll do something like that. And then if it's sum of some actual number, then we can go ahead and execute all this logic here. And so what we've done here is quite simple refactoring. We've just turned a partial function here into a total function by representing the failure case in the type. So now parseInt is a total function because there's no possible input that you can send it for which it will not return a value. And then down here, we'll do something similar. We'll just do this. We'll clean this up later, but for now, we'll just do something like this. So we'll assume we want to continue. And then inside the loop, we'll assume we don't want to continue. And the only case in which we don't want to continue is if the line of input was neither yes or no, in which case we'll just continuously evaluate this loop. So this is a little more resilient because we've changed this into a total function here, because in the event that we didn't get the yes or no that we wanted, we'll just keep asking the user until we actually get what we want out of that. So now we've taken the two examples of partial functions in this little application and we've converted them to total functions. So now there's no way this application can fail. There are no runtime errors. And this scales up to very large programs. If you do this in a big application like I've done before, it is almost unheard of to have a runtime error. No null pointer exceptions, no match errors, none of that stuff. It all just works, and this technique works very, very well. I'd even say at this point, it's idiomatic to represent failure in Scala or optionality with data structures like option and either, and to get away from using partial functions. I think it's a best practice in most Scala communities, maybe not all, but certainly most of them. So this is better. This is definitely an improvement. Obviously, we've added a whole bunch of stuff here, and there are ways to eliminate this duplication that we don't have time to. We'll improve this a little bit, but to push it all the way would actually take covering topics that we don't have time to. But we'll improve this somewhat, and I do think this is an improvement even in smaller applications. Maybe not this small, but even in relatively small applications, the guarantee of totality is very powerful. So we've still got lots of things which aren't functions, though. we've got things like this, and we've got things like readline, and we've got things like printline. And what these non-functions are doing is, for one, they're forcing us to reason about our software differently depending on where we are. So there are parts of our code base in which we can assume that everything is a total, everything is deterministic, everything is pure, and all our data is immutable. And so we can reason about that using type-based and equational reasoning. And then when we switch gears into other parts of our application, we have to change. We have to switch to procedural reasoning. So we have to reason about our program as a state machine, as if we were a Turing machine that's executing tape and simulating the state inside our head. And these are different ways to think about software. And having to switch between them is not very convenient, obviously. But then also we lose all the other benefits of pure functional programming that come from being able to look at types and know what our program does, being able to test more easily, being able to program without fear, and program without having to dive into the implementations of functions and so forth. So we would like to be able to fix that problem. How can we do that? Well, it seems pretty hard, and indeed it is hard. It took people a while to figure out how to do this. The answer turns out to be fairly simple, and that is convert an effect, an interaction with the external world, into a description of an effect. So instead of actually doing something like printline, what happens is you build a data structure. And I'm just going to call it IO. And it's going to have a single field here, which is going to be called unsafe run. And this single field is going to describe an interaction with the external world that produces an A. That's all it's going to do. It's going to describe an interaction with the external world that produces an A. And then there's a few handy things that are useful to have on a data structure like this, one of which is map. And this one says if we have this IO of A, by the way, is a description of an interaction with the external world that produces an A. But all it is a data structure, and it's an immutable data structure. So this is just like list or option or map or any of these other data structures. This data structure never changes, and it doesn't do anything. It's pure data. It's just a value. So what this map function does is it's going to return us a new IO of B, given the IO of A, and a way to get from an A to a B. So if we can get from an A to a B, then given an IO of A, we can get to an IO of B. And how do we do that? We create one description from another. So this description is going to look like this. It's going to do self unsafe run, and it's going to call F on that, converting the A into a B. And note here, we haven't actually done anything. We just created another description. We haven't run anything. We're just building data structures. And then another one that's going to be handy is this one here called Flatmap. And to do this, we just do self unsafe run, call unsafe run. That gets us an A. We feed that A into F, and we call unsafe run on that. And then we describe this interaction with the external world here. So we're not doing anything. And then one last bit of functionality that's going to be quite handy to have is a method often called point, which given an A is just going to return an IO of that A. And you can think of this as being a trivial interaction with the world. It doesn't actually need to interact with the world. It already has the value, and it's simply going to return the value. It's a pure IO in the sense that it has no effect. It describes no external interaction with the outside world. And this is actually all we need to do a bunch of stuff here. We can now model functions like printline in the following fashion. Create a description using this IO data structure, printing out that line of text to the console. And same for this function. And what these functions do is they build a value. This one builds a value of type IO unit. This one builds a value of type IO string. So given a line of text to print to the console, this one will build a description of an interaction with the outside world that prints that line of text to the console. And the same way for this one. So this one doesn't need any input. It's just going to immediately return a description of an interaction with the external world, which reads a line of input from the console. And this is all we need to make some pretty significant progress here. So what we can do here is, let's see if we can do this. We can change this to IO of unit. We do print line, and then print line, where we're going to change this to put stir line. And what this thing here does is exactly nothing. So this doesn't do anything. This does nothing other than returning an IO of unit. And if you print this out in the console, nothing's actually going to happen. If you run this in the console, nothing's going to happen. It's just going to build that value and return it. And that's okay. You don't need to do much. Ultimately, at the end of the world, what we're going to do is we're going to call this unsafe run function. And that's where we're going to execute this description of an interaction with the outside world, which has been composed from all these different operations. And what this buys us is it allows us to program in a pure functional style everywhere in our application, except at the top level. And at the top level, yes, we're going to be calling this thing here, which is not a function, and we're not doing functional programming at that point. But we only have to do it one place. So its effect is limited. How much it can infect the comprehensibility and composability and reasonability of our software is limited, because we can still do pure FP in the vast majority of our application. And in a language like Haskell, you don't even call this function because it's sort of built into the Haskell main function. So it's one step removed away from that. So this thing does nothing, which means that calling it will have no effect, which means we're not exactly replicating the previous program. What we have to do is we have to flatmap it. But rather than show you what that looks like, I'll just tell you to look up for comprehensions. And this gives you a more convenient syntax for interacting with stuff like this. So we're able to use for comprehensions in a way that reminds us of the imperative program. We can translate in pretty straightforward fashion this program into the corresponding pure functional equivalent. And then here we've got a problem here. So we've got some stuff here. How do we solve this problem? Well, this is a loop. And if you've done FP in small before, you know that loops can be translated into FP by using recursion. And in fact, this is exactly the same strategy that we're going to use here. So we're going to need a helper function here. So we'll introduce this function called game loop, which will take the string and it will return an IO of unit. And then we're not going to implement that now. We're just going to say, okay, we're going to do the game loop here with the name, and then we're going to yield unit. And then here we're going to take all this stuff. Got some stuff here. So we've got to recreate this machinery here inside our game loop. And we're going to, again, use a for comprehension here so we can take advantage of that sugar for map and Flatmap. And then let's see, what we're going to do here is execute one time. So I'm going to execute one time here. I don't need any explicit loop here. Later on, I'll go ahead and decide whether or not to call game loop again or to exit from the loop by not recursing. But now I'll just do. Now remember, we can't. If we're committed to pure functional programming, then we can't just perform this arbitrary effect here. This is not a function here. So that means we have to wrap it in IO. In fact, let me just pull that out. just going to call IO. Oops. What do we do here? We just converted this non-function into a value that describes the act of calling it at some later point. And then down here, what we're going to do is we're going to call num on next int of 5, and then we can't add one. We can't add one anymore because this returns an IO of an int, and we can't add 1 to an IO of int. That doesn't make sense. What we really want to do is map over its value and add 1 to that. So that's what we do. And that's that first line here. So we've done that. And now we need to do this part. So we'll ask the user, guess a number from 1 to 5. And then we need to parse the read line. So we're going to need to take this effect, and we're going to need to translate it here to like this. And then we can parse the out of the input. And this is going to take, this is the string, and this is going to give us the option of int. So we're going to need to do different things here, depending on whether this is this has been parsed successfully as an int or not. So I'm folding here over the option. This gives us the option. I'll fold over the option. And then in one branch, I'll do one thing. And in the other branch, they did enter a number. Got to do a different thing over there. And that different thing is going to be this here. I'm replacing all these by putster line. So what have I done here? Well, look, this is an option. I fold over that option to produce an IO. Actually, if you want to see the type here, I'm folding over this to produce an IO of unit. So I'm producing one of these pure values that describes an effectful computation. And in this branch, I'm going to say you didn't enter a number. And in this other branch, if they actually did enter a number because I successfully parsed it, then I'm going to I'm going to create this description of an action based on whether or not guess is equal to num. It's either going to be this or it's going to be this one over here. But in all branches, I'm returning an IO of unit. So I'm getting out of here nothing. I'm just running, basically parsing this for the effect of doing that. And so that takes care of this. It takes care of all this. And then we're stuck with this part here. So what I'll do is you want to continue. Here's what I'm going to do. I'm going to create a helper function because we need another loop. So we need another recursive function here. So I need a helper function here, which is going to check continue using the name. And then at the end of this for block, what I'll do is, let's see, what do I want to do here? This is the main game loop. So, right, what I'll do here is if the user wants to continue, then I'll call the game loop again with the name. Otherwise, game loop with a name returns IO of unit, so I have to return IO of unit over here. And I can do that quite simply calling IO point with unit. And then here I'm just going to yield unit. Keep in mind this function here is not tail recursive. This will actually, even in a stack safe IO monad, like ZIO or something like that, this will still eventually consume all heap. And the reason for that is Scala's for comprehensions add final map, so you can't finish in tail call position. So you can actually rewrite this though. You can solve that problem. But the user is not going to be so overwhelmed with our game that they keep playing it until they run out of heap. So we can trust this to work for toy purposes. All right, so now we just need this check continue function, which we'll do up here. And it's going to be a relatively straightforward translation of all this stuff. So let's just move that stuff up there. Check continue. It's going to first print out that do you want to continue? And then it's going to do the read line again. Well, we can't call to lowercase on an IO of string. So what we really want to do here is we want to map it. Map the string inside there to lowercase. And then we're going to have something that looks very much like what we did before, which is we're going to match input. If it's yes, then we'll say, we'll do IO point true. If it's no, we'll say they don't want to continue. And then in all other cases, we'll just continue the loop. And then here we'll return, I actually need this to be a Boolean. All right, so this will do what I need it to. And then down here, I'm using the return, I'm flat mapping over the return value of this IO. I'm flat mapping over that, and then I'm continuing the loop or not based on that. So let's take a look at this logic just one more time. So check continue will print out, do you want to continue? And then it's going to get a line of input, map that to lowercase. It's going to match over the input. If it's yes, it's going to return this pure program that just says true. If it's no, it's going to return the pure program that says false. Otherwise, it's going to keep the loop by calling itself recursively. And actually, even though this is not really any less code, I do think this is a bit easier to understand than all the while loops that we had before, especially if you're used to a recursive style. So there we have it. We have a purely functional version of the same program. And if you run this in the console, nothing's going to happen. You're just going to build this IO, which is a value that's been composed from all these other ones. It's an immutable value that's been composed from all these other things through map and flat map and point, the fundamental operations on this IO data type, map, flat map, and point. And then at the top level of your program, of course, you end up calling unsafe run, and that's when it goes through and actually executes all these descriptions of events, of external interactions with the outside world. So there you have it. You have the same program that we had up here. You have it in a purely functional style. And note that you don't actually have to build any of this stuff, of course. This stuff already exists in standard libraries. So you would never be building your own types for this, or even this stuff, like all these utility things, they already exist. Fortunately, Scala's FP community is quite industrious and has produced a lot of really great stuff to deal with effects. So you would never have to write any of this on your own. You can just leverage what's there in the ecosystem. But nonetheless, you can see for yourself that the principle underlying pure functional programming with effects is actually quite simple and involves merely translating effects into descriptions of effects and then running them later at the end of the world. Now, even though we're doing everything with pure functions, so there's not a single function here which is not total deterministic and free of side effects, even though we're doing that, there's still something that's a little unsatisfying about this solution. And I'll tell you what it is. Basically, inside here, we are embedding a hunk of code. This is not a function, remember. This is just a hunk of code. We're describing as a value a hunk of Scala code. And then we're passing around these hunks of codes and we're gluing them together in these different combinators. But as a hunk of code, we have no ability to see what's inside here. And the only thing we can do ultimately is run it. And also, this hunk of code can contain anything at all. So this is not actually providing us the full power of a purely functional approach, because once we get one of these things, the only thing we can do it is smash it together with other IOs, and then ultimately at the end of the world, we can run it. That's the only thing we can run it. And when we run it, it's actually going to perform effects. And so we're still going to have difficulty, for example, testing this application. How are we going to test it? Well, it has all the sorts of testing drawbacks that the original application does, which means you actually have to simulate input and output on standard input and output. Like you have to open up those and you have to feed in lines of text and so forth. It's very messy. And this is just a simple program. If you were interacting with external APIs or databases or whatever, then the problem would grow that much worse. So we still have a lot of testing problems. Also, we have some reasoning problems. We have some reasoning problems because the types of the hunks of code that you can stick inside this data structure are unlimited, which means if we see something like IO unit, there's no way we can tell, looking at the type, what that effect describes. The effect could describe anything because you can stick any hunk of code in here. So an IO of unit can describe any hunk of Scala code. In other words, to figure out what puts or line does, we actually have to dig into its implementation. So this doesn't provide the full benefits of functional programming, precisely because we're taking hunks of arbitrary Scala code, which are not functions, and stuffing them inside a data structure. So this is not the best thing that we can do here. We can actually do a lot better. And in order to do that, what we have to do is we have to give up our reliance on a concrete data type. Right now we're using this concrete data type. We have to develop the ability to abstract over things that look like IO, but which are not IO. And that's going to allow us to break up the world of infinite effects into more fine-grained things, such as the effect of console input-output, or such as the effect of random number generation. It's going to allow us to break those up into fine-grained effects so we can look at a type signature and we can know what it does. And then maybe using this approach, we're going to be able to test this better without actually having to interact with the real world. So to do that, we're going to introduce a type class, and I'm just going to call it program because we don't need anything fancy. And the type class is going to abstract over things that look like IO. IO is a type constructor, which is to say, if you look at this type here, it requires one type parameter. And if you look at this type here, it requires one type parameter. So F is a type constructor that takes one type parameter. So we're abstracting over things that look IO, so it has to look like this. Our type parameter has to have this kind annotation here. And we're just going to create functions that look like this. This represents a program that's done. It already has the value. There's nothing more to do. We'll just call it finish. And then we need a way to chain these things together. So if we have one program, and then we have a function that given the A from this program can give another program that produces a B, we can smash that back to a program of F of B. So this encodes chaining the output of one program into a function, which then returns another program, and then smashing that back down into the output of the second program. So this is sequential composition. We do this, we take the A, we feed it to this to get the next program, and then we run the next program. And then finally, of course, mapping, we need ability to, if we have an F of A and a function A B, which takes an A into a B, we need the ability to produce an F of B out of that. So that's our type class. And it's to have a, let's see, let's have a, 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 let here. Give us one of these things for an implicit that's in scope. This is just one of the ways to encode type classes in Scala. And then what we'll do here is we'll actually prove that we can write one of these things for I/O. We'll do it in the I/O companion object. We'll say implicit val program I/O equals new program I/O program. And then what we're going to do is copy paste these three methods and just change f anytime we see an f. We'll replace that with an I/O. And then here we will do, this becomes io.point. This is nothing more than Flatmap. This is nothing more than map. So Flatmap, you can see, encodes the ability to chain sequentially dependent programs together. Map is just, of course, map. And then finish is, in some sense, the return or the creation of a pure program that just has a value, doesn't actually interact with the outside world. And then we'll do one more thing, actually two more things. What we'll do is we'll create some syntax here. And we do that with implicit classes. This is going to be program syntax, and given an f of a, add some methods. This is how you do extension methods in Scala. It's going to add some methods, namely map, Flatmap. So now if we have an instance of this type class, this program type class in scope, then automatically any f of a value will be enriched with map and Flatmap methods. And of course, that's not super relevant for I/O because it already has these things. But once we start programming generically, once we generalize our program here to be able to work on things which are not necessarily I/O, we're going to need this capability in order to take advantage of this nice syntax that Scala gives us. So this syntax enrichment class, these extension methods are going to help us quite a lot. And then one more enrichment method here, which is this point thing, which given a program here, or finish, I guess I called it. All right. So is this enough? Well, not yet. You can see here we're using these put_stir line and get_stir lines, so we don't have yet enough to be able to generalize main here. We could start writing down here, and then Scala has context bounds you can use to say that I can work with any f for which there exists a program instance, an implicit program instance in scope. But we're not quite there yet because we're doing stuff other than map and Flatmap and point. We actually do three other things. We do put_stir line, get_stir line, and then we do this random thing. So let's take that same approach here. So we'll recreate the same machinery here and create more type classes to represent classes of effects. This is the sort of simplest possible set of effects you can imagine for building programs that are sequential and that terminate with some value, and that you can change the value inside produced by the program. So this is otherwise known as a monad, by the way. This is what a monad is. But for these other type classes, we're going to need something a little different. So we're going to need something like this for console, which gives us the ability to do put line and get line. And we'll add a little helper function down here. You can get an implicit console of f if that's in scope. You can get a handle on it. And then we'll do the following helper methods. Put line now actually can work with any console, any f for which there's a console defined for it. And what it's going to do is take that line of input and return an f of unit. And it's going to do that by doing console f put line on the line of input. Get line is going to be almost exactly the same. So these will be my helper methods here that I'll call directly. And then down here, I don't need these anymore. Instead, what I need to do is I need to create an implicit val for program here, and it's going to be console IO equals new console IO. I have to implement these two methods here. I've already done and just moved them there. Okay, so now I have the ability to describe using this type class something that can put string to the console and something that can get string from the console. So this is a bundle of capabilities, and it can be implemented for any F which is capable of providing something that's console-like input and output. Now I need one more in order to complete the refactoring, and that's this thing here. And I'll just call that random. And another trait called random. Given an upper bound, it's going to return an F in. Have that one capability. And then I need to create a helper function here. I can use this function at the top level. Finally, I need to create an implementation of this for I/O. And I don't need this anymore. So now I'm able to describe sequential programs composed from these three different operations. I'm able to describe console input output, and I'm able to describe random numbers, and I'm able to describe them all independently. So I'm using a fine-grained notion of effects here. And what this enables me to do is to take this so-called monomorphic program, which is specialized to my IO data type, which has very poor reasoning and testability properties, even though it's all still purely functional. I can make this polymorphic in any F that provides the set of capabilities required by my program. In this case, I need the programmability, sequential composition of programs. I need random, and I need console. And then I can produce an F. For any F that provides me these capabilities, I can go ahead and produce an F of unit. And how I do that, I just go in here and I change this to same thing. And then in here, let's see. Okay, so Yeah, the game loop, it uses all this stuff. Okay, to check continue though, and this is where we start to see dividends on fine-grained effects. Check continue doesn't use random number generation, just use sequential composition and console. And in fact, if we were a little more disciplined, we would factor out some of these things and just put them in standalone methods that would only use console. And we would be able to see here that these are programs that are polymorphic in any F that supports only just console input output. And so what you gain is the ability to, you regain the ability to look at these types and know what the program does just by looking at the types. We can say this one does sequential composition of programs and also does console input output. Anyway, we changed that. We have to change the return types here. And then we have to change a few things, such as anything that mentions I/O. We're moving away from I/O and we're introducing polymorphism. So we're not going to be able to use anything in I/O. I certainly can't use this anymore. And then, if I'm not mistaken, I think we got everything. Not quite everything. We've got a few more things to take care of. We've got where's finish defined? Oh, I just get stir line. Let me do that correctly. Oh, this should be string. And then we've got 94. We've got to introduce the F type parameter. And that's it. Okay, so now we've taken our program, which was hard-coded to I/O, the I/O data type, and we've made it polymorphic in any F, which supports the set of capabilities required by our program. And it's a very fine-grained set of capabilities, so we can look and we can see different parts of our program actually have different requirements. And this helps us understand our software a lot better because we can look at something and know, for example, that it only uses random number generation, or maybe only uses something else. So this allows us to understand our software by chunking up the set of all possible interactions with the external world into something we can more easily get our minds around. And also, because we have made this polymorphic in F, it doesn't have to be I/O. So in theory, we can substitute other data types. In fact, we might be able to substitute one, which actually makes it possible to test this thing without having to pipe data into and out of the process standard input and output, which is not going to be easy. Not even in this case, but certainly not in anything more difficult. And we haven't lost anything. We have not lost any capabilities because now we can recapture main I/O, which is going to be an I/O of unit, by simply calling main and instantiating I/O. And if we've satisfied the requirements, then we should be able to compile this. And yes, in fact, it does compile. So we've not lost anything. We've strictly gained capabilities. We've deferred knowledge of the concrete data type that we're using in our program to gain these various benefits here. So let's actually do that. Let's see if we can create a data type which doesn't store hunks of Scala code. This is going to be used for testing. And this is going to enable us to test this software without doing any interaction with the external world, any interaction whatsoever. It's not going to touch the external world. So to do that, we need two things. We first need some test data. So I'm going to use something like this. Test data is going to contain input just a list of strings, and then output is a list of strings, and then numbers, random numbers, a source of random numbers. This is just going to be a list of ints. And this is going to be our test data. And we're going to use this to simulate all the stuff we need to simulate. And then we're going to need another data type. We're going to need a data type that looks like this. This is going to be like IO, but not IO. I'll call it test IO. And just like IO, it has to be a type constructor of one type parameter. It represents a program that produces an A. How we're going to produce an A? Well, in this case, we're going to produce an A. If you give us test data, then we'll give you more test data and the A. So we can produce an A if you give us test data, and we'll produce more test data. And then just like IO, this thing is going to need a couple of functions here. And how we can perform this mapping operation is, look at this slot here. This slot contains an A. All we have to do is create another test IO that's going to feed it this T here. Is going to run it on the T. It's going to get back the tuple, and then it's going to change the A into a B. So one way to do that is to change that A into a B by applying F to it. And then what did I miss here? All right, AB. And then we need another function called Flatmap, just like we did for this one, which represents sequential composition. And what we're going to do is we're going to run this one self on T to get the tuple of test data and the A, and then we're going to take the A and we're going to feed it to this function to get back the test IO of B, and then we're going to run that on the second T. So we're basically threading test data through. We're feeding it to the first one, and then we're getting the new test data, and then we're feeding that to the second one, and so forth. We're threading state through our computations. And in fact, this is nothing more than the state monad. So you would never actually have to write this on your own. You can use this. It's in all the FP libraries. This is just the state monad with the state parameter fixed as test data. The final thing we need here is this function called point. It just says that. Okay, so we can't call, we would like to be able to call def main test IO and get back a test IO argument here. We're calling main on the test IO type. We can't do that because we don't satisfy the capabilities required of any F that has to call main. So we need to make sure that we provide instances for these three type classes. We can do that. The simplest way is just to copy paste this probably. So I'll copy paste this here, and then anytime I see IO, I'll just replace it by test IO, and that will work fine for this one. And then it's not going to work. It's not going to work so fine down here. we can at least see if we have the structure correct. And yes, in fact, we do. We have the structure correct. So now we need to figure out how we're going to implement these things. And one way to simplify the implementation here is to add some methods onto this one here. These are just helper methods that I'm going to call here in a second. And they're going to represent part of the functionality to do things like put_line. So if you call put_line a line of text, it's going to return you a tuple of test data and unit. To do that by copying this data structure, and the output's going to contain the new line prepended to the old output. And then the unit is just going to be unit. And then get_line is going to return a tuple of test data and string. It's going to do that by copying the input, dropping the first entry off the input. And then it's just going to take, and this will crash, but it will only crash if you didn't provide enough input inside the test data, and it will only crash inside your tests. And so you probably want your test to crash if you've got a bug in it. So this is going to be fine. And then we'll need one more thing here, and that's next int with this upper bound. And return a tuple of test data and int. And it's going to, the test data is just going to one off the nums. And then it's going to do the same thing here, nums head. And then that's going to make it easier to implement these functions here, because down here I'm just going to call test.io with the test data, test t put line with the line of input, and it's going to return me back the tuple of the test data and unit, which is what I need in order to satisfy this type signature. And then down here, I'm going to do the same thing down here. And then finally, and then this compiles. All right, so now I have created this data structure to represent test data, which has fake input and collects output, and also fake random numbers. And then it has the implementation of these type classes for this new test.io data type, which is, as I said before, the state monad. And so now it has the capability of composing programs sequentially, and also the capability of doing fake console input-output, and the capability of doing fake random number generation. So I'm getting pretty close here to something that I can actually use. I need maybe one or two more things. Let me add a eval function here that, given some test data, will return back the test data by running the whole computation. I'm just going to run it on T, and it's going to extract the first element of the tuple out. And then what I'll do is I want to render this in some sort of pretty fashion. So I'll call output. I need to reverse it because I'm prepending lines of output. And then I'll make string on it. Okay, and so now, all right. So now I have everything necessary to show you how this works. But let's create some example test data first. Test data is going to do, it's going to say, the input's going to be, so it's going to ask for the name first. So I'm going to do John, and then after it asks for the game, it's going to ask to guess a number. So I'm going to guess 1. And then after it does that, it's going to check if we want to continue. I'm going to say no. And then that's the end of the input. I don't need any more input. And the output is just going to start as empty. And then it will accumulate results over time. And then the random numbers, I just need one random number, and I'm going to say it's 1. So I'm going to, in fact, guess correctly. And then if we run this, what we're going to have to do is we're going to have to call, we call main test IO to get back our description of this computation. And then what we're going to do is call this new function I created called eval. We're going to call eval on the test example. And we're going to call the show results method on that to get back a string. So what I'll do is I'll actually drop down into the console here. I'll drop down into the console. And I'll call run test. And then what I'm going to do is I'm going to copy paste that output so you can see it. Oh, and I made one mistake. I entered in here 1, but then we add 1 to it. If you remember, we add 1 to it. We map over that and we add 1 to it. So I should have, if I wanted to win the game, I should have done 0. I'll just do 0. Anyway, if we enter in 0, we'll get back a slightly different response. We paste that in real quick. Okay. So now we get back the response I expected. This. What have we accomplished here so far? Well, we've gone from this program up here, which crashes in various places and in various ways for various reasons, and which is composed of mostly imperative stuff. We've gone from this program here to this other program, which is we have a lot of machinery, most of which you would not have to write because it already exists. We've gone to this program here, which is purely functional and doesn't use loops. It uses recursion. It doesn't use any partial functions. Everything uses total functions. Everything is a math function, so everything is total deterministic and free of side effects. And not only that, but these are polymorphic programs. These programs are not hard-coded to a single data type like IO. They can work with any F that support the capabilities that they require. So this gives us the ability to not only describe our effects in a very fine-grained fashion, but it gives us the capability to swap in different data types, including data types that do not interact with the external world. And we took advantage of that to write a test here, or at least the beginnings of a test, because what we've done here is we've run this on some test data. We've run the entire program on some test data, and we've collected that. This is totally pure. There's no effects happening here. And we did that just by supplying our own test IO data type, the state monad plugged in with test data, hard-coded with test data. And we're able to see here that we can interact with this program, at least fake interact with it, and we get back exactly what we expected. That program is working correctly, at least in this one example. This is actually very common. This style of programming in Scala is called final tagless or finally tagless. And it's a very common way to do effectful interaction with the external world because it gives you the benefits of polymorphism, which gives you testability, but also gives you reasonability. So you can look at a type signature and you can know something. You can constrain what these programs do. You know something about what they do just by looking at the types. If I had a fragment here which did nothing more, like this one here is a good example. So this is a function from the input. So I could literally call results here. And it's going to take the input, which is a string, and it's going to take the number, which is an int, and it's going to take the name, which is a string, and it's going to return IO of unit. And all I do is call this. And this only uses one thing. It uses put store line. So that's the only effect I need here. I can just call that down here. And got some compile errors. Oh. All right, so I can look at print results and I can know the only thing it does, the only effect it does, the only external interaction it has with the world is printing some stuff into the console. And note here, I did this refactoring. I didn't have to pay any attention to whether or not it's going to work. I know it's going to work. Refactoring functional programs is extremely robust. You can do this brainlessly, almost in your sleep. You can just copy paste things, inline them, and whatever. And it doesn't change the meaning of your programs. So I don't even think I need to test that. So we can do more though, and we should. In this presentation, we should do more, even though I'm not telling you to do this in real life with these toy examples. It doesn't make sense. But this program still has some problems. First off, we're throwing away lots of information early on. For example, we're converting what is essentially structured information into unstructured strings. And as a result, if we tried to create a test case out of this, we're going to get output like this. And we're going to have to parse this. And we're going to have to make sure that it's doing the right thing. Like we can look at this and we can know it's right. Maybe we just hard code this in the test, but this is not a great way to do things. Ultimately, we would be able to defer throwing away information as long as possible, push more power into the caller rather than the callee. And in this case, that would lead us down the path of taking this console type here and changing it. Maybe console's too powerful. Maybe we don't want the ability to print any line of text to the console. Maybe we only want the ability to print out a certain number of messages. And if you go through that exercise and you change all these different types here, you're going to get, let's see here, I'm doing it on time. Yeah, I don't have time to do this now, but I'm going to show you the end product of this. What you get here is something that looks like this. So you get, this is probably not correctly called console anymore, but instead of having the ability to print any line of text to the console, what it has the ability to do is print one of 1, 2, 3, 4, 5, 6, 7 different types of messages. And these messages are structured information. They're not strings, they're data types. And they capture all the things that you would expect. And then when you go ahead and run a program like this, you actually get structured information out of it. So instead of getting strings, you get a description of what it wants to print. And this has a couple of different benefits. First off, it's very, very easy to test because you can look at what the program is generating and you can verify that it's using the correct parameters. So you get the ability to test without having to parse random strings. And not only do you get that ability, but if you've ever worked in an international application, you know at some point you have to go through your application and rip out all those strings and replace them by keys. And in fact, that becomes trivial in this representation. So in this representation, when we're only allowed to print out so many different things and all of that is described by strong static types, then we're already able to easily take any of these messages and translate them into different languages. And there's a better technique you can use than to do it this way. This is just sort of hard coding it. This can actually be pushed into the type class. So you can actually have type classes that are responsible for refining from data types into strings based on locale. But all of that, I didn't do this to get localization out of it. But what happens in FP programs is because they are very generic and they defer destruction of information for as long as possible, and they try to invert the control so the caller always has control over things. They end up pushing a lot of decisions up the stack to the edges of your program. And then things like internationalization become very easy. Testing becomes very easy and straightforward. You don't have to do any messy tricks. You can just test stuff and so on and so forth. And so you can actually take, I'll upload this gist. This is the one that you should look at, even though we did almost all of this in the time that we had. And this is the one that you should look at because we've pushed this very, very far. We've gone from this messy imperative program to this one that's trivial to test, that doesn't necessarily need to interact with the external world, that can be internationalized for free if we want, and all kinds of other crazy stuff. So if we wanted to do remote console input, we wanted to have our program running on AWS, for example, we could do that because all we require from console is the ability to do put strline and get strline as defined here. In fact, not only could we do that, we could actually create a Scala.js application, and we can have part of it running in there, and it's using WebSockets, and it's implementing functionality using a totally different technique, using a different data type than IO or test IO. So what this gives you is flexibility to change and a strong static types that describe the behavior of your program, and the ability to use a uniform reasoning principles like equational reasoning and type-based reasoning over your entire program. And yes, this is most definitely overkill. All of this stuff, it is definitely overkill for this example. You should write this in Python or whatever. If you ever have a program this simple, just write it in some quick scripting language because it's just too easy to get it right. But these types of techniques, they pay off when you have large scale programs that are doing complex things that have to be maintained by lots of people over lots of time. And then there's just no comparison because the benefits that you get from this approach, you've seen some of the benefits, and I'm sure you can imagine even more benefits. This type of program, if you tell me some random way to modify it, because of how well structured it is, I'm probably going to be able to come in here and make that modification very easily and very cheaply, especially compared to the original one. I can extend this in all kinds of new crazy ways. I can test it very thoroughly and quickly without interacting with external systems. I can have a lot of confidence that this code is correct. And even though that doesn't matter at the small scale, at the scale at which big programs operate, when you start getting into tens of thousands of lines of code or hundreds of thousands or millions of lines of code, these types of benefits become immeasurable because the cost of maintaining those programs is enormous. And what a design like this does is it minimizes the cost of safe changes. You can make a change in a program like this, and you can know its implications by looking at the types and by using the compiler to help make sure that you don't screw things up. And then the additional flexibility it gives you in terms of reasoning and testing, all that stuff is definitely pays for itself, in my opinion, many times over when you reach a certain scale. So there you have it. FP to the max, stuff you should definitely never try at home, but I hope that you have all found this useful. If there are any questions, I will go ahead and take them now. All right. So can I upload the example programs? Yes, I will upload the example programs. I will upload refactoring and refactoring too. And that way you'll be able to see both what we did here interactively and then sort of the pre-coded version that I took a little further. I didn't take it all the way, by the way. If you wanted to do some exercises, then I would recommend first, think about getStir line. So this putStir line takes console out, which is structured source of information. Think about how you could change this so you tell it what you want, and it gives you that out again. So you tell it you want a yes or no, and then it gives you out a Boolean. Or you tell it you want a name, and it gives you out a name. Or you tell it out you want a number, and it gives you a number. So think about that. And then that gives you additional, obviously it makes it easier to test and so forth, but it gives you additional flexibility to implement this. You can actually put a GUI. At that point, you can put a GUI on top of this program. You can implement this for a data type that gives you a GUI in the browser, and you have all the information necessary to do that, which is really interesting. So I would do that. I would also try to do this properly, console out. So console out, ideally, this is a type parameter to this type class, and that way you can describe transformations between one console that has a data structure like this and between another one that can only support string. So I would make that final abstraction, just generalize over those types, and also take care of this problem here. So those exercises I'll leave you with. Let me return to the other questions I had. I've heard a lot about finely tagless and would like to know the details. In particular, how does finely tagless differ from what Haskellers would call MTL style? It doesn't differ at all. Haskell and MTL basically just means using the type classes and then deferring construction of the monad transformers until the end of the world. And that works very well. And it's basically what Scala programmers mean when they say finely tagless. Same with type class console. What's its canonical name? So I'm actually not sure console has a canonical name because normally people aren't putting that in a type class, even though I think it's a good idea to do. Won't the names of the extension methods collide with the names of IO instances methods? And no, it's actually not true. If Scala knows the concrete type, if it knows that it's IO, and you call map and Flatmap, then it will definitely use the methods on the object. The extension methods will not even be considered. It's only in the event that it's working with some generic F, which doesn't have methods called map and Flatmap, that it's going to use the extension methods defined by using that implicit conversion class. What's the canonical name for the program type class? That is monad. So the canonical name for the program type class, which we introduced here, this is called monad. And this other test IO type that we introduced down here, this is the state monad, but with the state specialized to this. You never have to implement this. You never have to implement any of this. Just use the state monad. I would have to talk about partial application of type constructors if I did that, and I didn't want to talk about that today. So, but if you were doing this in a real program, you would just use the state monad. There's a way to make it tail rect despite Scala's for comprehension limitation. How do we do this? So what we have to do is we have to write all the flat maps ourselves. An example would be, let's see, we have check continue. So what we do is we have to write this flat map, this flat map, this, and then we have to end here on one of these final things inside here, and then it will be tail recursive. However, Scala will add a final map. This down here will be translated into a final map, and as a result, this will not be tail recursive and will eventually consume all the heap space, even in a stack safe monad like ZIO or Monix task or something. So if you're doing looping for real, then don't use a for comprehension. The loops can't use for comprehensions. They have to use map and Flatmap, which means you don't get the nice sugar. This looks quite nice. It looks like an imperative program. You have to call map and Flatmap everywhere, but it's only a relatively minor inconvenience because it's only in the recursive parts of your program. Okay, the parameter of type unit to A. I know it's been a while since that question was asked, but let me cover it real briefly. So back here when we defined IO, we had this unsafe run function, which is describing a hunk of Scala code that when you apply it with unit, so this is a function 0 in Scala, you apply it with unit, and you're going to get back an A. So this is a description of a hunk of Scala code. That's all it is. And IO is a data structure that holds a description of a hunk of Scala code. And then obviously from this immutable data structure, you can create other immutable data structures like we've done in map and Flatmap and so forth this should be thought of as like list or option. It is the same idea here, except instead of storing values there, we're storing hunks of Scala code, and we're combining these hunks of Scala code into other hunks of Scala code, and we're just carrying around that description forever. And this is how we do arbitrary effects in a purely functional environment. All right, and then actually 3 more questions. One question is, why wouldn't you do this? and I think the answer is that for small programs, like let's look at the original program here. So this program here fits on a single screen, and it's, even though it's imperative and so forth, and you can't test it and whatnot, nonetheless, this is a small enough program that you can look through its lines of code, and you don't even need types. You could do this in JavaScript or whatever. Pick whatever language. You could do it in assembly language, and at a size this large, it doesn't really matter. You can just look through it and you can know it's right, or know it's wrong in this case. And even if it's not right, you can probably fix it pretty easily. So you probably don't need machinery for testing, and you don't need machinery to be able to figure out by looking at a function what it does and so forth. It's just too small. These are benefits. Functional programming shines best in large-scale applications. And it does that because there is definitely using types and type classes and using monad, all this stuff, it does carry with it some amount of syntactic overhead. It's mostly in the category of sort of benign overhead, in the sense that, like, if you just insert some random characters and delete something in here, you'll get a type error. That's not like you can screw things up, but nonetheless, you can see this is just more stuff. There's more stuff I'm typing here. And as a result, like, I had to introduce type classes to describe my different effects and so forth. And this is something that's not going to pay for itself unless you're working in large programs. Because you as a developer, when you pop open some function, you want to be able to look at it, and without inspecting its implementation, you want to be able to have some idea of what it does. And the way you do that is use precise types. But precise types has a cost. It's easier to describe generic things that can do anything. The function in Scala, the non-function of, like, partial function of any to unit, it can take anything, and it may or may not return, and it doesn't return anything. That's kind of the worst possible function you can possibly imagine, because in order to understand that function, you have to go down into its call stack and study the implementation of everything it calls recursively until the very end of the world and simulate that all in your mind. But if there's only one function like that in your application, if that is your application, if it's like here, this is a partial function from any to, actually a partial function from nothing to nothing, but it's just one function. It's the whole application. You can actually do that, and it's not too bad. But if you have to do this all over your code base, it slows you down, and you make lots of mistakes, and then you deploy mistakes in runtime, and those blow up, and your customers are unhappy, and your boss wants you to put in overtime, and you have to be on call sometimes. And it's a big pain in the ass. And the way you get away from that is you use strong static types that precisely describe the behavior of all your functions, and you reason about your code in a uniform way using equational reasoning and type-based reasoning. All right, so 2 more questions. Where should we start learning tagless final with some real-life examples? So I would Google for that term, Google for final tagless and finally tagless, and there's original papers on that. Also study MTL in Haskell. If you're familiar with Haskell, study MTL. And I'm pretty sure that this is being covered in Functional Programming for Mortals book by Sam Halliday. All right, what are limitations of monad transformers in Scala, and how tagless finals resolves that problem? All right, monad transformers are a method of composing effects. You can take a bunch of different effects and compose them together to get something that has the superset of all the effects. And that's quite handy. And unfortunately, it's very painfully slow in Scala. The JVM is not designed for executing functions, and it's not designed for the massive amount of heap that comes with monad transformers. Basically, in a program like this, every single statement in your program translates into a Flatmap, which involves at least one allocation plus dispatch on a function object. And then when you have monad transformers, If you have one layer, or rather a two stack transformer, then you've doubled the overhead of everything. And if you have four stacks, you've quadrupled it and so forth. So the overhead grows quite terribly. And the JVM is just not good at optimizing that type of code. It's not used to, for every single statement in your program, doing a bunch of allocations and a bunch of invoke virtuals. It's not used to doing that. And so it's not fast at it. It's extremely slow. And so monad transformers are not really a viable solution to composing effects in Scala. And ideally, you get away from that by composing effects like this. So in this example, I say I want F to support program and random and console. And then I end up at the end of the world, I have an implementation of this for I/O. So I have to pay the cost of I/O, but Scala has very fast I/O data types like ZIO, which are way faster than Future and have been very, very hand optimized. So that's relatively fast, and you end up backing your entire program. Even though it's described by fine-grained effects, all these global effects end up translating down into I/O. So you end up with the raw performance of I/O, which is as good as you can do in Scala. It's the best you can do in Scala, and it's good enough. There are very few applications for which it's not fast enough. But if you try to do this with monad transformers, like if you have here some base monad and then you stack on that random and it becomes untenable to do that. All right, any other questions? Great, it looks like that's it. So thank you so much for attending this presentation. I hope that you have gained an appreciation for the power of functional programming, and also like an appreciation for, yes, the fact there's more typing in functional programming. Not always, because when a lot of this stuff exists and when you're doing more complex things, like you're doing concurrency and parallelism and so forth, you can actually get by on far fewer lines of code. This notion of turning your programs into values and passing them around is very, very powerful and actually makes a lot of things very concise. But certainly for imperative stuff like this, it's generally going to make your stuff more verbose. But you do gain a lot of benefits out of that. And I hope you've seen, you're not going to be able to easily see the benefits of equational reasoning and type-based reasoning. You'll have to live with those for a while before you start becoming addicted to them. Because, all right, so yeah, you have to live with them before you really do become addicted to them. But some of the other benefits I think are pretty compelling. Just testability and being able to do almost anything without interacting with an external system or using mock libraries that involve bytecode instrumentation and lots of these edge cases. It's a huge pain to do mocking in the Java world. But basically what we did here is mocking, type safe mocking. No hacks. It's all principled. All this code is total. It's all made from actual math functions that are total, deterministic, and pure, and has a lot of benefits in large scale code bases. And even though these are not benefits that are necessary for a toy example, I do think this toy example nonetheless helps you see a path for how you take these things and you use them to solve very large scale problems, because it all looks like this. It's just more of the same. You have more type classes, but it's just a bunch of functions. They're all pure functions, and they use polymorphism in type classes in order to add structure to these polymorphic types, the minimal amount of structure necessary to solve whatever problem they're trying to solve. Thank you for attending, everyone.